Welcome to PreCalculus. But what is PreCalculus? PreCalculus Honors is a comprehensive course that weaves together previous study of algebra, geometry, and functions into a preparatory course for calculus. We will be reviewing some of the concepts you've learned in other math classes, but then we're going to be extending them and learning some other concepts that you haven't seen before. Let's find out what we're going to learn in PreCalculus. First, we're going to learn about function transformations. Right? In our diagram here, we have some examples of transformations in nature, in construction, in textiles. Mathematical shapes are found in architecture, bridges, containers, jewelry, games, decorations, art, and nature. Designs that are repeated, reflected, stretched, or transformed in some way are pleasing to the eye and capture our imagination. In PreCalculus, you will explore the mathematical relationship between a function and its transformed graph. We'll learn about radical functions. How far can you see from the top of a hill? What range of vision does a submarine's periscope have? How much fertilizer is required for a particular crop? How much of Earth's surface can a satellite see? You can model each of these situations using a radical function. Polynomial functions. Polynomial functions can be used to model different real-world applications, from business profit and demand to construction and fabrication design. We worked with polynomial functions in Algebra 2. We're going to extend our learning in PreCalculus. Trigonometry. Trigonometry is used extensively in our daily lives. For example, will you listen to music today? Most songs are recorded digitally and are compressed into MP3 format. These processes all involve trigonometry. Your phone may have a built-in global positioning system that uses trigonometry to tell where you are on Earth's surface. GPS satellites send a signal to receivers, such as the one in your phone. The signal from each satellite can be represented using trigonometric functions. The receiver uses these signals to determine the location of the satellite and then uses trigonometry to calculate your position. Many sinusoidal and periodic patterns occur within nature. Movement on the surface of the Earth, such as earthquakes and stresses within Earth, can cause rocks to fold into a sinusoidal pattern. Geologists and structural engineers study models of trigonometric functions and help them understand these formations. So a sinusoidal pattern, that's just a wave pattern. So for instance, on the top of that diagram where you see the yellow lines, right here, that's an example of a sinusoidal pattern. It's a wave pattern. Because it's repeating, it's also a periodic pattern as well. In Algebra 2, we worked with all 6 trigonometric functions, but we only graphed sine and cosine. We learned a little bit about the graphs of tangent. In PreCalculus, you'll graph all 6 trigonometric functions. You'll also be working with trig functions in very new ways and extending what you already know from Algebra 2 so that you're ready for calculus. Exponential and logarithmic functions. Exponential and logarithmic functions can be used to describe and solve a wide range of problems. Some of the questions that can be answered using these 2 types of functions include: how much will your bank deposit be worth in 5 years if it's compounded monthly? How will your car loan payment change if you pay it off in 3 years instead of 4? How acidic is the water sample with a pH of 8.2? How long will a medication stay in your bloodstream with a concentration that allows it to be effective? How thick should the walls of a spacecraft be in order to protect the crew from harmful radiation? All of these questions can be answered using exponential and logarithmic functions. We learned a little bit, actually we learned a lot, about exponential and logarithmic functions in Algebra 2. We're going to extend that knowledge in pre-calculus. Rational functions. Why does the lens on a camera need to move to focus on objects that are nearer or farther away? What's the relationship between the travel time for a plane and the velocity of the wind in which it is flying? How can you relate the amount of light from a source to the distance from the source? The mathematics behind all of these situations involves rational functions. A simple rational function is used to relate distance, time, and speed. More complicated rational functions may be used in a business to model average costs of production or by a doctor to predict the amount of medication remaining in a patient's bloodstream. We worked with rational functions in Algebra 2. We'll extend that knowledge in pre-calculus. Function operations. It's important to understand functional relationships between variables, since they apply to the fields of engineering, business, physical sciences, and social sciences, to name a few. We'll be combining functions. We'll be finding the inverses of functions. We'll be substituting a function for a variable. You've substituted a number for a variable in Algebra 1. Now, in pre-calculus, we're going to substitute a whole function for a variable. And it'll allow us to do some new things with functions. Systems of equations and inequalities. Many real-world situations involve too many variables to be modeled by a single equation. For example, weather depends on the relationships among many variables, including temperature, wind speed, air pressure, and humidity. So to model the weather and forecast a snowstorm like the one pictured below, scientists use many equations, each having many variables. Such collections of equations, called systems of equations, work together to describe the weather. Systems of equations with hundreds of variables are used by airlines to establish consistent flight schedules and by telecommunication companies to find efficient routings for telephone calls. Okay? So, if it wasn't for systems of equations, it would be just impossible for an airline, for instance, to schedule all of its flights. Right? So that because you can't have two airplanes landing in the same runway at the same time. They use systems of equations to make that happen, right? So that airlines arrive at different times, the airplanes arrive at different times at different runways. We won't be working with hundreds of variables, but we might work with 3 or 4. Conic sections. Conic sections correspond to the different graphs of functions where x and y are variables, where the x and y variables are squared. There are 4 different kinds of conic sections: circles, ellipses, parabolas, and hyperbolas. You worked with circles in geometry. You worked with parabolas and hyperbolas a little bit in Algebra 2. Ellipses will be a new function for us. These functions are called conic sections because they correspond to the cross sections of different cuts on a cone. So depending on how you cut a cone, you get a different cross section. The properties of conic sections make them useful for many real-world applications. For instance, a reflecting surface with parabolic cross sections concentrates light at a single point. This property of a parabola is used in the construction of solar power plants, like the one in California pictured above. Right, so all of those are solar panels, and notice how they're shaped in the shape of a parabola. They're positioned, I should say, in the shape of a parabola. Polar coordinates. So this will be a new concept for you. Polar coordinates are a different way of representing points and lines in a plane. Typically, one uses the x value of a pair of coordinates to figure out how far to the left or right to go, and then uses the y value of a pair of coordinates to determine the height. In polar coordinates, however, One number gives an angle from the horizontal, and the other gives the length of a line. Polar coordinates are helpful for graphing different curves, including circles and spirals, like the one shown at the left here. It's easy to use polar coordinates to graph rounded shapes, such as circles and spirals. Using rectangular coordinates, that's what we're used to on the x and y coordinate system, is like describing a location in a city by saying it's at the corner of 2nd Street and 4th Avenue. These directions would help a taxi driver find the location. But what if you were in a hot air balloon? That wouldn't be so helpful. We can also describe this same location as the crow flies. We can say that it's 1.5 miles northeast of City Hall. We have a length, 1.5 miles. We have a direction, northeast of City Hall. These directions would help an airplane or a hot air balloon pilot find the location. Sequences and series. The amount in a bank account at the end of each month, mortgage payments, and the amount of an annuity are sequences. The formulas that generate these sequences drive our economy. They allow us to borrow money to buy our dream home closer to graduation than to retirement. Many patterns in nature can be modeled by sequences. For example, the Fibonacci sequence describes such varied natural patterns as the growth of a rabbit population, the arrangements of leaves on a plant, the arrangement of scales on a pineapple, and the intricate pattern in a nautilus pictured above. We'll learn about sequences and series in PreCalculus. And finally, limits, a preview of calculus. Calculus is used in modeling numerous real-life phenomena, particularly situations that involve change or motion. Limits are used in finding the instantaneous rate of change of a function, as well as the area of a region with a curved boundary. We'll be introduced to these concepts in PreCalculus, and they'll be interwoven all throughout this course. So I'm so glad to have you here in PreCalculus. We're going to learn a lot, and I hope you're excited. Bye for now.